Hello everyone. Welcome back to CS422, Theory of Computation. You probably have heard about the Millennium problem in computer science, the P versus NP problem, which if you can solve that, will earn you not just the most prestigious award in the area, kind of like the computer science counterpart to a Nobel Prize, but also $1 million as donated by the institute. So what is this Millennium problem about? It's about the question whether P equals NP or not. And we have talked about these complexity classes for many sessions. Chapters 4 and 5 are about P and NP, and we have discussed some decision problems and been able to show that they are complete for the complexity class NP. They are the hardest problem. So if you can show any of these problems to be solvable in polynomial time, if you can design a polynomial time algorithm for any of these problems, then it means that all the other problems will also have polynomial time algorithms. And conversely, if you can prove that just any arbitrary of these problems is not solvable in polynomial time, then all the others can also not be solved in polynomial time, and thus the two complexity classes are different. So actually, that means you have a great choice of freedom, right? So you can pick any NP complete problem and either prove that it is not decidable in polynomial time, or find a polynomial time algorithm for any problem. It doesn't really matter which one, because they are all equivalent after all. And yet, nobody has been able to answer that question, to prove or disprove that. For over 50 years now, the seminal paper that started this direction of research dates, Cook's paper dates back to 1971, and the Levin paper a little bit later. So why is that so? Why is it so hard to solve that question, whether P is equal to NP, whether NP complete problem can or cannot be decided in polynomial time? And one reason for that is what we've talked about at the end of last class, in which I would therefore like to review again. Namely, it seems that all the proof techniques that we have employed so far have a certain property, namely they are relativizing. They work also for Oracle computation, for Oracle bypass program. And as demonstrated by Baker-Gill and Soloway, any such Oracle or relativizing proof cannot solve the P versus NP problem. And this is kind of a kind of exciting. This is a new direction of research. It's kind of like meta computer science. It's about proving that something cannot be proved in a certain way. It's a counterpart. It's a continuation of the famous 1931 Gödel statement that there exist claims in number theory that are true, but provably cannot be proven. That's another example of a meta statement. Provably cannot be proven. And the Baker-Gill and Soloway statement is also a similar of this meta nature, saying that P versus NP provably cannot be proven, at least with respect to using relativizing proof techniques. Or put differently, as Sherlock Holmes said, exclude all the impossible explanations. And here we have a wide range of impossible approaches to P versus NP, and consider the most improbable instead. That's Sherlock Holmes, and in our setting, that means look at the remaining techniques, whether however improbable they might be, they are going to solve the P versus NP problem. So imagine yourself like, I'm going to say like 10 or 20 years from now, and somebody has been able to solve the P versus NP problem, then we can clearly say how he or she has not been able to solve it, which method did not work, and thus some of the remaining method will have been the key to this resolution, looking from the future back, future to. So what is the Baker-Gill and Soloway theorem? Let us recall that. So here you see, right, it's about, yes. Proof methods for solving P versus NP, but also for solving NP versus P space and for solving P versus P space, which are also open problems. As you recall, P versus exponential time, this we have been able to show that exponential time is strictly more powerful than polynomial time, but for the intermediate classes, it is remains open. And we've seen many proof techniques relating these classes. So we proved that P is a subset of NP, and then NP is a subset of P space. And reconsidering the proofs, which I really strongly urge you to do, these proofs are all relativizing. They all also work with respect to any arbitrary oracle A. So P with oracle A, remember our generic definition of a relativized complexity class, is contained in NP with oracle A, is contained in P space with oracle A. So all the statements and the proof techniques that we used to establish that small hierarchy also work with oracles. They also relativize. And therefore, these proof techniques cannot be used to solve the P versus NP problem, as the Baker-Gill and Soloway theorem demonstrates, which we'll recall in a minute. Another example of a relativizing statement and a relativizing proof techniques is Savage theorem. Remember, we proved that NP space, non-deterministic polynomial space, is the same as deterministic polynomial space. And again, the proof works and carries over to oracle computation. So for any fixed oracle A, NP space with oracle A is the same as P space with oracle A. And again, please use the opportunity to review Savage proof from that perspective, and hint the only part of the computation in Savage proofs really arises at the ground case of the induction of the recursion, and one step in the configuration graph, whether this is a valid transition or not, whether there exists an edge or not in that huge but implicitly stored graph, whether there exists an edge between two vertices, that is where the actual computation comes in. And the same applies also to oracle computation, as you are strongly recommended to convince yourself of, not me convincing you, but you yourself. So these are all examples of relativizing proof techniques. And now Baker-Gill and Soloway in 1975. Soloway is already at that time was a famous logician and set theorist, and he knew all the techniques called forcing that were used in set theory. And when he started collaborating with Baker&Gill on computer science topics, this collaboration across from computer science and logic, that gave rise to this seminal theorem. Right, so what is the Baker-Gill and Soloway theorem? It consists of two statements. The first says that there exists an oracle relative to which P is equal to NP, which means that we cannot prove P different from NP using relativizing proof techniques, because relativizing proof technique for P different from NP, relativizing means that it would also carry over to oracle and would thus imply that P with oracle A is different from NP with oracle A, which is a contradiction. to the first statement of Baker-Gill and Soloway, which says there exists such an oracle. And the second statement of Baker-Gill and Soloway says that the same is also true. We cannot prove P is equal to NP with relativizing proof techniques because there exists an oracle for which, relative to which P is provably different from NP. So this is other essential two meta statements of the Baker-Gill and Soloway paper. And the proof of statement A is actually not very hard. Namely, we can use any p-space complete oracle A. And for any p-space complete oracle A, P with relative to this oracle is the same as p-space, right? If we can get such a powerful oracle as access, then we can solve every problem in p-space by simply deferring the computation to the oracle. And same for NP with p-space oracle. Again here, the non-determinism can be simulated by p-space, and p-space with a p-space oracle is still only p-space. So that this, when A is p-space complete problem, then these two are equal. For example, quantified Boolean formula, we recall we proved to be such a p-space complete problem. So that was kind of easy. The second claim is more involved and surprising maybe. Actually, so the statement of the second item says that there exists an oracle. So Baker-Gill and Soloway proved and constructed such an oracle using advanced diagonalization method. But what we're going to do, we're going to prove a stronger statement, namely, not only does there exist such an oracle, but almost every oracle has P different from NP. Namely, if we pick a random oracle, then with probability 1, this oracle makes relativizes to be different from NP. So, well, probability 1, of course, does not mean for every possible oracle, but it means that the set of oracles for which P is different from NP must have measure 0 and must therefore be a very small set. Keep in mind that we can recover the non-relativized case always by using the trivial oracle, for example, the empty set as an oracle. Then P with empty set as oracle is the same as P, and similarly NP with empty set oracle is the same as NP. So, but the empty set oracle is just one oracle among uncountably many possible oracles, right? So the space of all possible oracles is the space of all subsets of natural numbers, of which we initially saw that they are uncountably many. Now, what is a random subset of natural numbers? That definition needs to some clarification. And random here means we take every natural number independently and either place it in the oracle or keep it outside of the oracle based on an independent flip of a fair coin, 50-50. For every natural number x, we put it into the oracle or we don't put it in the oracle with probability 1/2 independently at random. If they proceed to perform that process as a thought experiment, of course, because it takes infinitely long to throw infinitely many coins for each natural number, of course. But in the end, this creates a random subset of natural numbers. You can also imagine that random subset of natural numbers as an element of the bare space of infinite binary sequences, right? So the Cantor space of infinite binary sequences. So consider an infinite binary sequence and consider this as a characteristic function. So those positions in the sequence, those indices, those natural numbers where the sequence element is 1, can be means that the element, the index, is an element of the set of natural numbers B, whereas those with the value 0 means that the corresponding element is not in B. And in this way, we can identify bijectively subsets of natural numbers with elements of Cantor space of infinite binary sequences. And just a second. Yes. Right. So that's another way of looking at random oracles by picking a random element in Cantor space. There's a strengthening of the item C. So item C is obviously stronger than item B, and it was proven 6 years later by Bennett&Gill. So Gill is the same author as in the earlier paper. So it's a strengthening, and this was later strengthened throughout a succession of papers and results. For example, proving NP different from P space with respect to random oracle and so on. And it's arguably the latest and world record result on this is a similar statement for the entire polynomial hierarchy. So remember, the polynomial hierarchy considers P, NP, co-NP, and then the relativized class P with NP oracle, NP with NP oracle, co-NP with co-NP oracle, and so on. So it's this infinitely long hierarchy, which is all contained in P space. And again, we don't know whether this hierarchy is strict, whether climbing up the next level really increases the power, which is a generalization of the P versus NP question. And Rossman and others have shown in 2015 that with respect to any random oracle with probability 1, this hierarchy is infinite, so it climbs up infinitely high, and it particularly that implies the claim from item C. So we're not going to prove this. This is pretty famous, actually, the Rossman and others paper, item D. So we're not going to prove that here in this lecture, but we are going to prove item C, which then implies item B. And we did so actually last time. So this is actually kind of to recall that and to add some additional insights. So here's a statement that we're proving on this slide. And here's actually the kind of a decision problem that we're going to prove to be in NP with respect to oracle B, but provably not in P with oracle B. And this decision problem, of course, depends on the oracle B. And the first observation that this is clearly can be decided in NP with oracle B, because it's already formulated in this syntactical form with a witness. The witness here is the Y, and the verifying problem, which is polynomial time decidable, because this universal quantifier observes that the universal quantifier only ranges over polynomial range, and thus polynomial time algorithm can check every possible candidate Z, because they're only polynomially many, whereas it's not feasible to check every possible witness Y, because there are exponentially many of these. And and checking this inclusion is easy to do when you have oracle access to B, because it's defined in terms of B anyway. So this is obviously in NP with B oracle. And the difficult, challenging part of the proof is to show that it is provably not solvable in P with oracle B. And so the intuition behind this complicated formula is the following. So we divide the array of natural numbers into these kind of steps. They're big steps, 4 to the n, 4 to the n plus 1, and so on. So always growing geometrically with a factor of 4. And then we subdivide these big steps into smaller steps, each of increasing by n. So 4 to the n plus n, 4 to the n plus 2n, and so on up to 4 to the n plus 2 to the n minus 1 times n. So there are exponentially many of these so small steps that that's the point, they fit nicely into the big steps. So the last small step is still far from the next big step. That's how the steps are kind of designed in purpose, so that we later get some independence. Recall that the entries in the or random oracle B are depend on independent random choices. And so any point here on this line is kind of an independent event, whether it belongs to the oracle B or not. And so making the steps disjoint assures them to be independent. And now we're going to look at intervals between the small steps. So this is an interval of n elements, and we have similar intervals here and here and here and here. And we've performed some calculations of the properties. So the defining property basically says whether there exists one small step, right, enumerated by this witness, somewhere here among the exponentially many small steps, whether there exists one for which the interval is entirely contained in the oracle. Okay, so does there exist kind of a one of these exponentially many intervals which is entirely contained in the oracle? That's a kind of question that is formalized in this decision problem. And we've calculated some probabilities, namely the probability for an individual element to belong to this oracle is, of course, 50-50, right? It's dependent by current flip. So the probability for an entire interval of n elements all to be in the set means that all these coin flips must come up heads. And since they're independent, that means the probability is the product of the individual probabilities, and therefore is 2 to the minus n, right? So here this, for all z, there are n of these possible values for z. This must belong to B, and independence says, right? So every entry in this interval belongs to the oracle or not, independently with 50-50 probability. Therefore, the entire interval to belong to the interval means that all these coin flips, all these independent events must come up out in the same way, and thus the probabilities multiply 50-50. N times means 2 to the minus n. So put differently, this is a very small probability. And one way of looking at this construction or understanding why do we consider this admittedly strange and artificial decision problem is we can also consider it as a way of looking at the intervals as the events, not single numbers, but these small intervals. But we want these probabilities to be very, very small, exponentially small, 2 to the minus n. So a different way of looking at this is by considering oracle B, where the intervals are kind of the events, and not natural numbers are events, but intervals. But these events happen with not with constant probability, 50-50 or any other constant, but with exponentially small probability, 2 to the minus n. And it may be helpful to look at this perspective, look at these decision problems from these two perspectives and move back and forth between both. Right. So this is a very small probability. On the other hand, the probability that there exists such an interval, exponentially many possible intervals, although each one has a very exponentially small probability, since there are many possible choices, candidate intervals, the probability for some interval to belong to this oracle is actually a constant, right? So you can see that from simple expectation, right? If you repeat a experiment with a probability 2 to the minus n for 2 to the n times, then the expectation says that actually that with that is the expected number of intervals that are entirely contained in the oracle is 1. Let me say that again. So we have every oracle has probability 2 to the minus n to contain this interval, probability 2 to the minus n to contain this interval, probability 2 to the minus n to contain this interval. But the expected number of intervals that are thoroughly contained is 1, right? So that's simple expectation calculations. But here we're not interested in the expected number of intervals, but in the probability for one interval to be entirely contained in this. And this is calculated by means of the exponential function. Then let's consider the complement event from this one. The probability that this specific interval is not contained, that's of course 1 minus 2 to the minus n. And therefore, the probability that all these intervals, none of them are contained, that's the complement of this event. Again, we can use independence. So the probability that for all y, the interval is not contained is therefore the product of the individual probabilities. So 1 minus 2 to the minus n, which you see here, raised to the 2 to the n, because the 2 to the n such so that the probability that for all these y, this holds, is 1 minus 2 to the minus n to this. And then returning, applying again complement probabilities, that is 1 minus this. And this is actually the formula for the series converging to the exponential function. So in the minus here translates to, the exponent minus n translates to 1 over 2 to the n, and therefore this converges to 1 over n, and the 1 minus remains. So this is a constant probability. That's a message here. So we have exponentially many events. Each one is exponentially unlikely, but the probability that at least one of them holds is constant. So every element x of this form, we're not talking about x's of other form, is contained in the random oracle with a constant probability. It's up to the, this is what makes it really challenging for a polynomial time algorithm to test that, right? So if this were a very sparse set, then maybe it's easier if they are few, or if they are almost everything x is contained, then again maybe it's easier, but it's really almost 50-50. 63% is it's, as long as it's a constant probability, it's challenging intuitively. And now let's make that formal. So we make a proof by contradiction, and right, the algorithm will of course use the oracle B, make oracle calls, and Since by hypothesis, the algorithm we consider arbitrary algorithm, right? So this is the key to complexity theory, arguing about any possible algorithm, as long as it's polynomial time algorithm, can also make at most polynomially many queries to the oracle. And the queries also have this form, right? So the statement that we are going to prove is that the probability of this complicated event is bounded from below by a constant. Now, what does this complicated event mean intuitively? There are two cases. The first case says that x, we're considering again input x of the form 4 to the n. The probability that this input does not belong to the decision problem LB, yet the algorithm with oracle B accepts it. That's upward, right? Upward error means accepted. So that means that the algorithm makes a mistake, right? The algorithm with oracle B accepts X, although X does not belong to the decision problem. So that's one way for an algorithm to make an error. And the second part is the second way for an algorithm to make an error. This is about the case where the algorithm rejects, which is here indicated by the downward arrow, although the input X belongs to the decision problem. So this are the two types, the two cases where the algorithm A with oracle B makes an error. And this is a random event because the oracle B is, as you recall, a random oracle. So we fix the algorithm, but we consider a random oracle, and we consider the probability for the algorithm to make a mistake on this random oracle for the fixed input. Now, let me say that again, because it's indeed subtle, but important. So we have kind of three objects that we want to talk about. Algorithm A, oracle B, and input X. And the way we argue about them, we fix an arbitrary algorithm A. We consider arbitrary but fixed input X, and we consider random oracle B. And we talk about the probability that this algorithm A, when equipped with this oracle B, makes a mistake on deciding whether X belongs to the decision problem LB or not. And we're going to show that this probability is positive. It's bounded from below. It's at least 0.1. Okay, this is what we're going to show. The probability that the algorithm A on input X with a random oracle B makes a mistake. So this is a probability that the algorithm errs on input X with respect to random oracle. And in order to estimate this probability, let's look at the two kind of cases of error separately and show that each one, or at least one of them, has probability greater than 0.1. So of course, the probability will depend on the algorithm, right? Consider, for example, an algorithm which always accepts, okay? An algorithm which always accepts, it doesn't even look at the oracle. Then the probability for this algorithm to accept here is 1, whereas the probability for this algorithm to reject is 0. And conversely, also consider an algorithm which always rejects, then the situation is reversed. And we're going to show that in either of the two cases, however the algorithm performs, at least one of the two cases will occur with probability at least 0.1. And to this end, let's first consider the second case, okay? And let's express that using conditional probabilities, which is what you see here. The probability that the algorithm rejects although the input X belongs to the decision problem LB, can be expressed as the product of a conditional probability with the conditional itself, right? So that's simply the definition of conditional probability. And let's now suppose that's a case that the probability for the algorithm A with random oracle B to reject X would be at least 50%. Okay, and later we're going to consider the case where the probability is actually less than 50%, and we're going to show that in either case, in the first case where the probability for the algorithm to reject is at least 50%, then we're going to show that the second event occurs with at least probability 0.1. And in the other case where the probability that the algorithm rejects is less than 50%, it means that the probability that the algorithm accepts is at least 50%. And then we're going to argue that also in this case, the overall probability to make a mistake is at least 0.1. And therefore, the probability will be at least 0.1 in either case. That's what we're going to prove. And currently we're proving the second case, and we suppose that this part of the conditional probability, the last factor, is at least 50%. It doesn't really matter whether it's 50%, must be just one constant. Now, what does that mean? That means, if we consider random oracle and consider the execution of that algorithm, since it's a polynomial time algorithm, it can query at most polynomially many of these intervals in the oracle, right? Polynomially many among the exponentially many. So the algorithm is supposed to reject, that's a conditional probability, and it rejects after having looked only at polynomially many of these exponentially many subintervals. And so there's a high probability, no, it's definitely true for large enough n, since polynomial grows smaller than exponential. For large enough n, the algorithm will definitely have missed some of these subintervals. So what does it mean to have missed some of these subintervals? That means if we change the oracle at this position where the algorithm at these subintervals kind of introduce or put an entire subinterval into the oracle subinterval which the algorithm has not queried, didn't have time to query, then the algorithm behavior will remain unchanged. And we say that again, that's an important argument. Technically, it's a continuity argument. So the polynomial time algorithm can query at most polynomially many entries in that oracle. So if we as adversary argument, change the oracle B and insert an entire interval, small interval at a position which the algorithm does not query, and then repeat and re-execute the same algorithm again, then it will behave the same way again, right? So because all the oracle queries will be answered in the same way, because the oracle queries that the algorithm makes will be made again, and we don't change those. We only change the oracle at places where which the algorithm does not query. And by doing that, by introducing an entirely small subinterval, that means that there exists now after our change, that there exists such a witness, so that after our change, suddenly X belongs to this modified oracle, let's call it B prime. Yet the algorithm still rejects and thus makes an error. So we have constructed now with kind of, as an adversary, we've constructed an oracle on which the algorithm makes a mistake. This is a kind of a crucial step of the oracle original Baker-Gill and Soloway proof. But here we want to consider probabilities. And to this end, let us refine and see that since the algorithm queries only polynomially many parts in the oracle, we have, as adversaries, we have plenty of choices where we can modify the oracle without changing the algorithm's behavior. Actually, we have exponentially many choices left. Among that overall exponentially many choices, only polynomially have been kind of taken away and fixed by the algorithm. So there are still exponentially many left, and therefore taking a random oracle, repeating kind of the coin flips for recreating the random oracle while fixing the polynomially many entries that the algorithm looks at, and only flipping the coin for the other ones, still gets a constant probability for an oracle where the actually X belongs to, provably belongs to the decision problem LB, yet the algorithm still gets to reject it. So that in this case, still the probability is at least 0.1. It's just an arbitrary number, really 0.1. The important part is it relies on polynomial to be strictly smaller than 2 to the minus n minus 1, half of the exponential. And that only works for sufficiently large n. So for small n, all these estimates are actually wrong. But for sufficiently large n, the estimate that we claim here are true. In the first, actually in the second case here. And the first case can be handled similarly. Express that as a conditional probability times the probability that the algorithm accepts. Suppose now in this case that the probability for the algorithm to accept is at least 50%, right? So if it's less than 50%, then we're in the case that we've just covered. If the probability is at least 50%, then make the same analysis and argument again. The algorithm accepts, but it has looked only at polynomially many entries. And now probably the algorithm, if it's conservative, will have looked at entries that are actually present. But for most of the oracles, this is simply not true. And one can again apply adversary construction to fool the algorithm and refine that to show that with high probability, constant probability, the algorithm will make a mistake, will still reject, although will still accept, although by construction we have now removed entries, intervals from the oracle, and thus have forced X to not be an element of this decision problem. So to conclude, in both cases, if this conditional probability is at least 50%, or if this conditional probability is at least 50% in both cases, the probability for the algorithm to make an error on input X is at least some constant like 0.1. And now we've performed this analysis for fixed input X. So what is the probability that the algorithm works correctly on all inputs X? Well, that's a complement probability to error, right? So 1 minus p to the with index 4 to the n, that's a probability that the algorithm operates correctly on input X equal 4 to the n. And operating correctly on all inputs, that's again by means of this random process, that's the product of all these probabilities, which is, since every probability is less than 0.9, well, all sufficiently large probabilities are less than 0.9, right here. The product of 0.9 infinite product is 0. So with probability 0, does the algorithm operate correctly on all possible inputs? So it's probability 0 that the algorithm really decides that. And since we talked about an arbitrary polynomial time algorithm, that means every polynomial time algorithm works correctly with probability 0. And now at the final step, we need to consider the event that there exists an algorithm. And since there are only countably many of these algorithms, that probability is bounded by the countable sum of 0, which is still 0. So this is how we make the whole argument independent of the algorithm, right? So first we showed that any algorithm makes an error with probability, and then we show that the probability for that there exists an algorithm is also 0. So that concludes proof of the Bennett&Gill strengthening of the Baker-Gill and Soloway theorem, showing that with probability 1 relative to this random oracle, P is actually different from NP, and therefore all relativizing proof techniques cannot show P equal to NP. So yes, that concludes our recap and review of the last lecture of the end of chapter 5, right? Yes, so for sufficiently large n as n tends to infinity. So we talked about p-space complete problems, quantified Boolean formula, in 3 conjunctive normal form, and a graph problem with this 2-player problem. We showed that all these problems can be solved in polynomial space, usually using some sophisticated recursive algorithm. Recursive algorithms are good for memory saving, although they might require recalculating intermediate properties that we've already determined before, but which we decided to forget and not store in order to save memory. And this is fits well with a recursive algorithm approach. So we showed this, all these problems can be solved in polynomial space, and we showed them to be complete for polynomial space using reduction, a master reduction, strengthening of the Cook-Levin reduction, now making use of all these quantifiers in QBF and making use of the 2 players in the graph decision problems. So this is kind of the p-space counterpart to NP completeness. We proved Savage's theorem that non-deterministic space is up to polynomial as powerful as polynomial space, up to quadratic polynomial. So there's the memory kind of counterpart to P versus NP is kind of thus settled up to polynomial. And we proved the strengthening to NP versus co-NP, namely Immermann-Saleptony. Here the gap or the growth is not even polynomial, it's linear. Non-deterministic space and co-non-deterministic space are the same up to polynomial vector. In both cases, there was this subtle but important technical condition that the function f describing the growth of memory must be space constructible. It's a condition which I have not really elaborated in detail, but there are also counterexamples that says when f is artificial arbitrary, then this may or may not be the case. Anyway, then we talked about Oracle computational complexity. We've relativized the complexity classes P, NP, P space, and we've considered the polynomial hierarchy. First, syntactically, with alternating quantifiers, constant number of quantifier alternations, where QBF had a variable number of quantifier alternations, and semantically, meaning that we consider NP as an oracle, then NP to NP as an oracle, and so on, for semantically meaning for oracle while plus programs. And finally, we investigated why it seems so hard to solve the P versus NP problem, namely because of the limitations of relativizing proof techniques, which provably cannot prove P either equal to NP nor P different from NP, as exhibited by the Baker-Gill and Soloway construction and randomized refinement due to Bennett&Gill. So that concludes chapter 5. And as announced before, this is where we also conduct a quiz. So here's the quiz.